Hello there, and welcome to Cosmic Dreams Universe. I'm so glad you found your way here tonight. Maybe the world felt too loud today, too certain about itself, too fixed and solid and demanding. Or maybe you are the kind of person who finds rest not in emptiness, but in wonder, in the particular quietness that comes from thinking about something so large and so strange that your smaller worries simply dissolve into it. Whatever brought you here, this moment is yours. You have nothing left to do tonight, nothing to check, nothing to carry forward into tomorrow. So let yourself settle. Let the day fall away from your shoulders. Let your breathing slow just a little, the way your body knows how to do when you finally give it permission. Because tonight, we're going somewhere very small. Smaller than a cell, smaller than a molecule, smaller than an atom. We're going to the level of the universe, where the rules that govern everything you can see and touch simply stop working. Where the comfortable certainties of ordinary life give way to something far stranger, far more beautiful, and far more unsettling. We're going into quantum physics, the science of the very small. The science that describes how electrons behave inside atoms, how light interacts with matter, how particles appear and disappear and tunnel through walls, and exist in two places at once, and know about each other across vast distances, faster than anything should be able to travel. Quantum physics is the most successful scientific theory ever created by human beings. Its predictions have been tested to extraordinary precision, and they have never once been wrong. And yet, more than a century after its discovery, the physicists who work with it every day still argue about what it means, what it is really saying about the nature of reality, whether the universe at its deepest level is random or determined, or something stranger than either. Tonight, we'll drift through quantum physics the way you drift through a dream, not trying to grasp every detail, not holding on, but letting the ideas wash through, each one opening something quietly in the mind, each one leaving behind a residue of wonder that will still be there when you wake. Some of what you hear tonight will be strange, genuinely uncomfortably strange, but strange in a way that is also beautiful. Strange in a way that somehow, by the end, may make you feel not smaller, but larger. Not more confused about the world, but more awake to its depth. And before we begin, if these slow, curious journeys help you rest, if they give your mind something wide enough to drift into, consider liking and subscribing to Cosmic Dreams Universe. It helps others find their way here, one curious mind at a time. Now, let's go small. Everything you can see is mostly empty space. This is where quantum physics begins, not with equations, not with experiments, with a fact about the chair you're sitting on, the bed you're lying in, the walls of the room around you. They are almost entirely empty. An atom, the basic unit of matter, consists of a tiny, dense nucleus at its center, surrounded by electrons. But the nucleus is extraordinarily small compared to the atom as a whole. If you were to scale an atom up until its nucleus was the size of a marble, the electrons would be orbiting roughly a kilometer away. Everything in between is empty space. Not empty in the sense of a vacuum we might understand. Empty in the sense of nothing. No matter. No substance. Just the quantum fields that govern how particles interact and the space through which they move. The reason solid objects feel solid is not because they are full of matter. It is because of electromagnetic repulsion. The electrons in the atoms of your hand repel the electrons in the atoms of whatever you touch. It is this repulsion, this quantum mechanical force between electron clouds, that gives matter its apparent solidity. When you touch something, you're not actually touching it, not in a physical sense. The electrons of your skin and the electrons of the object you're touching never actually contact each other. They push against each other from a tiny distance, and you interpret that pushing as the sensation of touch. The solid world is an illusion, not in a mystical sense, but in a very literal, very physical one. The matter around you is almost entirely empty space, structured by forces we cannot see, producing the appearance of solidity through repulsion rather than contact. And inside that mostly empty space, the story of quantum physics unfolds. The electron does not orbit the nucleus the way a planet orbits a star. This was one of the first great puzzles of quantum physics, and the solution to it changed everything. In the early 20th century, scientists had discovered that atoms consist of a positive nucleus surrounded by negative electrons. The natural assumption was that electrons orbit the nucleus the way planets orbit the sun, a miniature solar system held together by electromagnetic attraction rather than gravity. But this model had a fatal flaw. Classical electromagnetism tells us that a charged particle moving in a curved path must radiate energy. It emits electromagnetic radiation as it accelerates. And if an electron is orbiting a nucleus, it is continuous. The resolution to this paradox came from quantum mechanics, and it required abandoning the idea of the electron as a particle with a definite location and trajectory. In quantum mechanics, an electron does not orbit the nucleus in the way a planet orbits a star. Instead, the electron exists as a probability cloud, a spread-out quantum state described by a mathematical function called the wave function. The wave function tells you not where the electron is, but the probability of finding it in any given location if you were to look. The electron is not here or there. It is smeared out. It is a probability distribution wrapped around the nucleus, existing in all its possible locations simultaneously until an observation or measurement forces it to appear in one specific place. Atoms are stable because of this. The lowest energy state of an electron in an atom is a specific quantum configuration that does not radiate energy. The electron does not spiral inward because it is not moving along a classical trajectory at all. It exists in a standing wave pattern, stable, energetically grounded, filling the atom space with its probability cloud. This is the first great strangeness of quantum mechanics. Particles are not points moving through space. They are probability distributions. They do not have definite positions until they are observed. Reality, at the quantum level, is fundamentally probabilistic. Light is both a wave and a particle, and so is everything else. This is called wave-particle duality, and it is one of the central puzzles of quantum mechanics, one that has never been fully resolved, even today. In the 19th century, physicists established that light is a wave. It diffracts around obstacles. It interferes with itself, producing patterns of bright and dark bands that only waves can create. It has a wavelength and a frequency and a speed. It was one of the great triumphs of classical physics, the understanding that light is an electromagnetic wave. And then, in 1905, Albert Einstein showed that light is also a particle. He was trying to explain the photoelectric effect. When light shines on certain metals, electrons are ejected from the metal surface. But the energy of the ejected electrons does not depend on the brightness of the light. It depends on the frequency. Turn up the brightness and you get more electrons, but not faster ones. Increase the frequency of the light and the electrons come out faster, with more energy. This makes no sense if light is a wave. Waves transfer energy continuously, and brighter waves should transfer more energy per unit time. But it makes perfect sense if light is made of particles, discrete packets of energy called photons. Each photon carries a fixed amount of energy determined by its frequency. Brighter light just means more photons, not more energetic ones. Higher frequency means more energetic photons. Einstein's explanation was radical. It implied that light, which had been proven to be a wave, was also somehow a particle. This won him the Nobel Prize in 1921, and it opened the door to quantum mechanics. But the strangeness goes further. Not just light, but everything exhibits wave-particle duality. Electrons, protons, atoms, even large molecules have been shown to exhibit interference patterns characteristic of waves when their behavior is measured carefully enough. Matter is not particles. It is not waves. It is something for which we do not have a good everyday word. Something that behaves like a particle when you measure its position and like a wave when you observe its motion. Something that is both and neither, depending on how you look. This is not a puzzle that has been solved by saying the right words about it. It is a genuine feature of reality that has been confirmed by every experiment ever designed to test it. The universe, at its deepest level, is not made of particles or waves. It is made of quantum things, for which our classical concepts are inadequate descriptions. The double-slit experiment reveals something deeply troubling about the nature of observation. This experiment is so fundamental to quantum mechanics that the physicist Richard Feynman called it the only mystery. It contains, he said, the heart of quantum mechanics. The setup is simple. You have a source of particles, electrons or photons or atoms. In front of the source, you place a barrier with two narrow slits cut in it. Behind the barrier, you place a detector screen that records where particles arrive. If particles are classical objects, like tiny bullets, the result is simple. Some particles go through the left slit, some go through the right slit. On the screen behind the barrier, you see two bands of impacts, one behind each slit, exactly what you would expect. But that is not what happens. Instead, the screen shows an interference pattern. Many bands of light and dark alternating across the screen. The same pattern you would see if you sent waves through two slits. Waves interfering with each other, reinforcing where their peaks align and canceling where a peak meets a trough. This happens even when you send particles through one at a time. One electron fired through the apparatus, it lands somewhere on the screen. One at a time, the electrons arrive, each one landing in a seemingly random location. But as the pattern builds up, electron by electron, the interference pattern emerges. Each individual electron passing through the apparatus alone somehow interferes with itself. The only way to explain this is if each electron passes through both slits simultaneously. If each electron is, in some sense, a wave spreading through the apparatus, passing through both slits at once, interfering with itself and only collapsing to a single point when it hits the screen and is detected. Now here is where the story becomes truly strange. What if you add a detector to the slits? What if you set up an instrument to observe which slit each electron passes through? The interference pattern disappears. Completely. Entirely. The moment you set up a measurement to determine which path the electron takes, it takes only one path, and the pattern on the screen becomes the classical two-band pattern of particles, not the interference pattern of waves. The act of observation, the act of measuring which slit the electron passes through, changes the outcome of the experiment. The electron behaves differently when it is being watched, not because the measurement disturbs the electron physically, though that is part of what was initially thought, but because the quantum state of the electron is fundamentally different, depending on whether information about its path exists or does not exist. It does not matter whether any human being looks at the measurement. What matters is whether the information is, in principle, available anywhere in the universe. The universe itself seems to care whether information about a quantum event exists. This is deeply troubling. It suggests that reality at the quantum level is not objective in the way we normally assume, that the state of a particle is not a fixed, definite fact independent of observation, that observation, measurement, the existence of information
plays a fundamental role in determining what is real. The uncertainty principle is not about measurement limitations. This is a common misunderstanding, and clearing it up makes the principle even stranger. In 1927, Werner Heisenberg formulated the uncertainty principle. It states that there is a fundamental limit to how precisely certain pairs of properties of a particle can be known simultaneously. The most famous pair is position and momentum. The more precisely you know a particle's position, the less precisely you can know its momentum. The more precisely you know its momentum, the less precisely you can know its position. The common misunderstanding is that this is a practical limitation, that if we had a gentle enough measurement device, we could measure both position and momentum precisely without disturbing the particle. But the uncertainty principle is not about measurement disturbance. It is a fundamental feature of quantum reality. A particle does not have a precise position and a precise momentum simultaneously. These quantities are genuinely indeterminate, not just unknown, but undefined, until a measurement is made. Before measurement, the particle exists in a superposition of many possible positions and momenta. It is the act of measurement that causes one specific value to be realized. The uncertainty is not in our instruments. It is in the particle itself. This has profound consequences. It means that perfect knowledge of a quantum system is impossible, not because we are not clever enough, but because there is nothing to know. The information simply does not exist until an observation creates it. It also means that empty space is never truly empty. Because of the uncertainty principle, even a perfect vacuum, a region of space with no particles in it at all, has an irreducible quantum uncertainty in the energy of the electromagnetic field that fills it. This uncertainty manifests as virtual particles, pairs of particles and antiparticles that spontaneously appear and annihilate in times so short they can never be directly observed. This quantum vacuum fluctuation is not hypothetical. It has measurable consequences. The Casimir effect, observed in laboratories, is a force between two very closely spaced metal plates.
caused by the suppression of certain vacuum fluctuations in the space between them. The plates are pushed together by the pressure of the vacuum outside, where the full range of fluctuations is present. Empty space pushes. The vacuum has energy and structure. Nothingness in the quantum world is not nothing. Quantum superposition is perhaps the most famous strangeness. A quantum particle can exist in a superposition of multiple states simultaneously. Not one state or another, both or all at once. And the superposition is not a matter of ignorance, of not knowing which state the particle is in. The particle is genuinely in all the states at once, until a measurement forces it into one. The famous illustration of this is Schrödinger's cat. Erwin Schrödinger, one of the founders of quantum mechanics, proposed a thought experiment in 1935. He imagined a cat placed in a sealed box with a device that would kill the cat if a single radioactive atom decayed. Radioactive decay is a quantum event described by quantum mechanics as a superposition of decayed and not decayed states simultaneously. The atom is in both states until it is observed. If quantum superposition applies at the level of the atom, Schrödinger argued, then by the same logic it should apply to everything connected to the atom, including the killing device and the cat. The cat should be in a superposition of alive and dead simultaneously, until someone opens the box and observes. Schrödinger intended this as a reductio ad absurdum, a demonstration that quantum superposition cannot simply be extended to macroscopic objects without producing absurdity. But the uncomfortable truth is that this argument has never been fully resolved. Physicists continue to debate where exactly the quantum world ends and the classical world begins. Why we never observe macroscopic superpositions. Why the cat is always either alive or dead, never both. The leading explanations involve a process called decoherence, the idea that macroscopic objects, like cats, interact constantly with their environment, with air molecules, with photons, with electromagnetic fields. This constant interaction causes quantum superpositions to rapidly break down, to become what appears to be a definite classical state. The cat cannot maintain its superposition because it is constantly being measured, in a sense, by everything around it. But decoherence does not fully solve the measurement problem. It explains why we cannot observe macroscopic superpositions. It does not explain why, when a measurement occurs, one specific outcome is realized rather than another. The randomness at the heart of quantum measurement remains, as far as we know, irreducible, fundamental, not the result of hidden variables or incomplete knowledge. The universe, at its deepest level, chooses its outcomes at random, with probabilities that can be precisely calculated, but with no deeper reason for why one outcome rather than another is realized in any specific instance. Quantum entanglement may be the strangest fact in all of physics. When two particles interact in certain ways, they can become entangled. Their quantum states become linked, correlated, in a way that persists no matter how far apart the particles move. And when one entangled particle is measured, the other instantly reflects that measurement, no matter the distance between them. Einstein called this spooky action at a distance. He was deeply uncomfortable with it. He believed it proved that quantum mechanics was incomplete, that there must be hidden variables, some deeper level of description in which the outcomes of measurements are determined in advance, and the apparent randomness and the apparent instantaneous connection are both illusions. He was wrong. In 1964, the physicist John Bell showed that any hidden variable theory must make predictions that differ from those of quantum mechanics, in a way that can be experimentally tested. And since then, many experiments have been performed, increasingly sophisticated and increasingly careful. Every single one has confirmed the predictions of quantum mechanics. Entanglement is real. The correlations between entangled particles are stronger than any classical explanation can account for. The universe is genuinely non-local. The state of one particle is genuinely connected to the state of another, regardless of distance, in a way that cannot be explained by any information passed between them. But here's the part that is important to understand. Entanglement does not allow information to travel faster than light. When you measure one entangled particle and get a result, you cannot use that result to send a signal to someone measuring the other particle. The results of measurements on entangled particles are correlated, but the individual results are still random. You cannot control what result you get. You cannot encode a message in randomness. Entanglement is real. Non-locality is real. But the universe is arranged so that this deep connection between distant particles cannot be used to send signals, cannot be used to communicate, cannot be used to violate causality. The universe is non-local at the quantum level, and yet relativity and causality are preserved. How these two facts coexist is one of the deepest unsolved puzzles in physics. There are many interpretations of quantum mechanics. None is universally accepted. This is important. Quantum mechanics as a mathematical framework works perfectly. Its predictions are accurate. Its calculations are precise. No experiment has ever contradicted it. But the question of what quantum mechanics means, what it is actually saying about the nature of reality, is unresolved. And physicists disagree about this more than they disagree about almost anything. The Copenhagen interpretation, the oldest and most widely taught, was developed by Niels Bohr and Werner Heisenberg. It says, essentially, that quantum mechanics describes the outcomes of measurements, and that asking what is happening between measurements is meaningless. The wave function is a tool for calculating probabilities, not a description of physical reality. There is no quantum world. There is only an abstract quantum description, in the physical world we observe when we make measurements. Many physicists find this interpretation unsatisfying. It seems to place measurement and observation at the foundation of physics without explaining what measurement is, or where the boundary lies between the quantum world and the classical world of measurements and observers.
The many worlds interpretation, proposed by Hugh Everett in 1957, takes a radically different approach. It says that the wave function never collapses. Every time a quantum measurement occurs, every possible outcome actually happens. The universe branches into multiple versions of itself, one for each possible outcome. In one branch, the cat is alive. In another, it is dead. In one branch, the electron went through the left slit. In another, the right. There is no randomness. There is no collapse. There is only the wave function, evolving deterministically, branching endlessly. In the many worlds interpretation, every quantum event that could happen does happen, in some branch of the universal wave function. The universe is constantly splitting into parallel versions of itself, each one as real as all the others. This interpretation has attracted serious attention from physicists and philosophers. It is mathematically elegant and takes the formalism of quantum mechanics completely seriously, without any additional assumptions about collapse or measurement.
But it comes with a cost. An unimaginably vast number of parallel universes constantly proliferating, each containing its own version of every event that has ever had more than one possible quantum outcome. Then there is pilot wave theory, also called de Broglie-Bohm theory. It proposes that particles do have definite positions and trajectories at all times, but are guided by a real physical wave, the pilot wave, that threads through space and guides their motion. In this interpretation, quantum mechanics is deterministic at a deeper level. The apparent randomness comes from our ignorance of the exact initial positions of particles. Pilot wave theory reproduces all the predictions of quantum mechanics exactly. It has no observers, no collapse, no branching universes. Particles always exist and always have definite positions. The cost is non-locality. The pilot wave must be instantaneously sensitive to changes anywhere in space, including across the entire universe. And there are others. Relational quantum mechanics, cubism, consistent histories, each one a different attempt to make sense of the same mathematical framework, each one emphasizing different aspects, each one solving some problems while creating others. After more than a century, the question of what quantum mechanics means remains open. The most successful scientific theory ever created by human beings describes reality with extraordinary precision, and no one fully agrees on what that description is describing. Quantum tunneling allows particles to pass through walls, not metaphorically, literally. In classical physics, a particle that does not have enough energy to cross a barrier cannot cross it. A ball without enough energy to roll over a hill rolls back. This seems obvious. This seems like common sense. In quantum mechanics, it is wrong. Because a quantum particle is described by a wave function, and wave functions do not sharply stop at barriers. They decay exponentially inside the barrier, becoming smaller and smaller, but they never quite reach zero. And on the other side of the barrier, the wave function picks up again, small but non-zero. This means there is always a small but non-zero probability of finding the particle on the other side of the barrier, even if the particle does not have enough energy to classically cross it. The particle can tunnel through. Quantum tunneling is not a theoretical curiosity. It is responsible for some of the most important phenomena in physics, chemistry, and technology. Nuclear fusion in the Sun depends on quantum tunneling. The protons in the Sun's core do not have enough thermal energy to classically overcome the electromagnetic repulsion between them and fuse, but they tunnel through the repulsive barrier with sufficient frequency to power the Sun. Without quantum tunneling, the Sun would not shine. Radioactive decay is a tunneling process. Alpha particles, trapped inside atomic nuclei by the strong nuclear force, tunnel out through the barrier that confines them. The decay rate, the half-life of a radioactive element, is determined by the probability of this tunneling event. Scanning tunneling microscopes use the tunneling of electrons between a sharp metal tip and a surface to image individual atoms. The current that flows through the tunnel junction is exquisitely sensitive to the distance between tip and surface, allowing atomic scale features to be mapped with extraordinary precision. The transistors in every computer chip you have ever used rely on quantum tunneling in their operation. Modern electronics exist because particles can pass through walls. The quantum world is not separate from the everyday world. It is the foundation of it. The strange rules of quantum mechanics produce the reliable behavior of classical physics that we experience every day, but only because of processes like tunneling that have no classical analog. Quantum spin has no classical equivalent. Electrons, protons, neutrons, and other fundamental particles have a property called spin. It is in some ways analogous to the spin of a top or a planet. Spinning objects have angular momentum, and so do particles with quantum spin. Spinning charged objects create magnetic fields, and so do particles with quantum spin. But quantum spin is fundamentally different from classical rotation, and the differences reveal how deep the quantum world goes. Classical spin is continuous. You can spin a top at any rate you like, in any direction. You can slow it down or speed it up gradually. Its angular momentum can take any value. Quantum spin is discrete. An electron, for example, has a spin quantum number of 1/2. When you measure the spin of an electron along any axis, you get one of only two possible results: spin up with value positive 1/2 in units of the reduced Planck constant, or spin down with value negative 1/2. No intermediate values, no continuous range. Two options, always. This is strange enough, but it gets stranger. The spin of an electron is not defined until you measure it. Before measurement, the electron is in a superposition of spin up and spin down. And when you measure the spin along one axis, you learn nothing certain about the spin along a perpendicular axis. Measuring spin in the x direction disturbs the spin in the y direction completely. And the discreteness has profound consequences. It leads to the Pauli exclusion principle, which states that no two fermions, particles with half-integer spin like electrons, can occupy the same quantum state simultaneously. Two electrons in an atom can share the same energy level only if they have opposite spins. And this principle is what gives atoms their structure. It is why electrons fill shells in atoms, each shell having a limited capacity. It is why matter is stable. It is why chemistry exists. The Pauli exclusion principle is why you cannot walk through walls. Not directly, but through a chain of quantum consequences. The electrons in your atoms and the electrons in the wall cannot occupy the same quantum states. This is what produces the electromagnetic repulsion that makes solids feel solid. Quantum spin, a property with no classical analog, no intuitive counterpart, no way to visualize it as something familiar, is responsible for the structure of the periodic table, the stability of matter, and the solidity of the physical world. Quantum computers exploit superposition to perform calculations in new ways. A classical computer processes information in bits. Each bit is either 0 or 1. At any given moment, a bit has a definite value. Computations proceed by manipulating these definite values through sequences of logical operations. A quantum computer uses quantum bits, called qubits. A qubit can be in a superposition of 0 and 1 simultaneously. This is not the same as saying it is either 0 or 1 and we don't know which. It is genuinely both with certain probabilities, until measured. A single qubit in superposition is not more powerful than a classical bit. But the power of quantum computing comes from what happens when you have many qubits entangled with each other. Two entangled qubits in superposition do not simply represent twice the information of one qubit. They represent a superposition of all four possible combinations: 0, 0, 0, 1, 1, 0, and 1, 1, simultaneously. Three entangled qubits represent all 8 possible 3-bit combinations at once. 10 entangled qubits represent all 1,024 possible 10-bit combinations simultaneously.
A quantum computer with enough qubits can, in principle, process all possible inputs to a problem simultaneously, exploring a vast computational space in parallel in ways that classical computers cannot. This does not make quantum computers universally faster. They are not better than classical computers at everything. But for specific problems, particularly problems involving searching large spaces, finding patterns in large data sets, simulating quantum systems, and breaking certain cryptographic codes, quantum computers have the potential to be exponentially faster than any classical machine. Quantum computers are still in their early stages. Current machines have tens to hundreds of qubits and are prone to errors caused by decoherence, the same process that prevents Schrödinger's cat from remaining in superposition. Building stable, error-corrected quantum computers with thousands or millions of qubits is one of the major engineering challenges of our era. But the principles are sound, and the first demonstrations of quantum advantage, computations performed by quantum computers that would take classical computers impractically long times, have already been achieved. The strange logic of quantum superposition, the same logic that makes electrons exist in all their possible positions simultaneously, is being harnessed as a computational resource. The strangeness of the quantum world is becoming useful. Quantum field theory is the deepest description of reality we have. Quantum mechanics, as we have been discussing it, is the quantum mechanics of particles, of electrons and photons and protons. But this framework, powerful as it is incomplete. It does not naturally incorporate Einstein's special relativity. It does not fully account for the creation and destruction of particles, which happens constantly in particle physics experiments. The framework that does all of this is quantum field theory. In quantum field theory, the fundamental objects are not particles, but fields. Fields that pervade all of space, everywhere, at all times. The electron is not a particle that moves through space. It is a ripple in the electron field. A photon is a ripple in the electromagnetic field. Every type of fundamental particle is a quantum of excitation in its corresponding field. These fields fill the universe. They interact with each other. When two particles interact, what is really happening is that their corresponding fields interact, exchanging quanta, creating and destroying excitations. The standard model of particle physics is a quantum field theory. It describes all the known fundamental particles and three of the four fundamental forces: the electromagnetic force, the weak nuclear force, and the strong nuclear force, in terms of interacting quantum fields. It has been tested to extraordinary precision and has never been found to be wrong. The mathematics of quantum field theory predicts the magnetic moment of the electron to 11 decimal places, and the measured value agrees with this prediction to 11 decimal places. This is the most precisely tested prediction in the history of science. And yet, quantum field theory is not the final word. It does not include gravity. General relativity, Einstein's theory of gravity, describes gravity as the curvature of space-time, and it cannot be straightforwardly incorporated into the quantum field theory framework. The unification of quantum mechanics and general relativity, the creation of a quantum theory of gravity, is the great unsolved problem of theoretical physics. String theory, loop quantum gravity, and other approaches have been proposed. None has been experimentally confirmed. The deepest level of physical reality remains unknown. The quantum world communicates in the language of probability.
Let your body sink deeper now. Let the ideas settle around you like falling snow, each one touching down and staying, without urgency, without demand. In the quantum world, you cannot predict with certainty what will happen next. You can only predict the probabilities of different outcomes. The wave function of a quantum system contains all the information that can be known about the system, and what it encodes is not certainties, but probabilities. This is genuinely random, not pseudo-random as computer-generated random numbers are, not random because of hidden variables we cannot access, random in a fundamental, irreducible way. When a radioactive atom decays, there is no reason, no cause, no deeper fact that determines when it decays. It simply decays at a random moment with a probability per unit time that quantum mechanics can precisely calculate. The universe, at its foundation, is not deterministic. It does not have a fixed future.
The future is not written. It is genuinely open, genuinely undetermined, right down to the quantum events that occur in the atoms and molecules of your own brain as you think. Some physicists and philosophers are troubled by this. Einstein famously refused to accept it. God does not play dice with the universe, he said. But the dice are being rolled. They have always been rolled. At every quantum event, in every atom, in every molecule, in the crackling electrical activity of every synapse in every brain that has ever thought, the universe chooses randomly among its possibilities. And yet, out of this randomness, order emerges. Predictable chemistry, reliable physics, stable matter. The universe at the macro scale behaves in ways that are, for all practical purposes, deterministic, even though the quantum events at its base are random. The randomness averages out. The probabilities, multiplied across vast numbers of particles, produce the reliable behavior that classical physics describes. Randomness produces order. Probability produces reliability. The universe builds stable structure from the irreducible randomness of the quantum world. Quantum biology suggests the quantum world reaches into living things. For a long time, it was assumed that quantum effects, while fundamental at the level of atoms and electrons, were irrelevant to the messy, warm, wet complexity of living systems. Biological molecules are large. They are surrounded by water. They are subject to thermal noise that should cause quantum coherences to decohere rapidly, washing out any quantum behavior before it could play a role in biochemistry. This assumption may be wrong. Evidence has been accumulating that certain biological processes exploit quantum effects in ways that evolution has harnessed over billions of years. Photosynthesis, the process by which plants and bacteria convert sunlight into chemical energy, appears to use quantum coherence in a remarkable way. When a photon is absorbed by a photosynthetic molecule, the energy must travel through a network of molecules to reach the reaction center where it is converted to chemical energy. Experiments have suggested that this energy transfer occurs with extraordinary efficiency, close to perfect, far better than any classical random walk through the network could explain. The proposed explanation involves quantum coherence. The energy, rather than hopping randomly from one molecule to the next, may exist simultaneously on multiple paths through the network, feeling all possible routes at once and finding the most efficient one. It may be quantum tunneling its way to the reaction center. If true, this means that plants have been running a form of quantum computation since long before human beings existed. Photosynthesis, the foundation of most life on Earth, may be a quantum process. Bird navigation may also involve quantum mechanics. The European robin, among other migratory birds, is sensitive to the Earth's magnetic field with extraordinary precision. The leading theory for how it achieves this involves a quantum process in the bird's eye, in a protein called cryptochrome. A photon of light striking the protein creates a pair of electrons in a quantum state where their spins are entangled. The way these electron spins evolve, and ultimately how the protein changes shape in response, is sensitive to the orientation of the external magnetic field. The bird's quantum eye reads the Earth's magnetic field by observing quantum spin dynamics. If this is correct, birds navigate using quantum entanglement. They are not just biological creatures that obey quantum mechanics as everything does. They are biological creatures that have evolved to exploit quantum mechanics as a tool. And the human sense of smell may have a quantum component as well. The prevailing theory of smell for decades was that the shape of an odor molecule determines how it binds to smell receptors, in the same way a key fits a lock. But some researchers have proposed that olfactory receptors may be sensitive not just to molecular shape, but to molecular vibration. And molecular vibrations are quantum mechanical phenomena. If this is correct, we smell at the quantum level. Our awareness of the scent of a flower, of coffee, of rain on dry ground may have its roots in quantum physics. The quantum world may not be confined to physics laboratories and particle accelerators. It may be alive in the biology of every living thing.
The measurement problem remains unsolved. We have spoken about it several times tonight in different contexts, but it deserves a moment of its own. Because it is the deepest puzzle in quantum mechanics, and possibly in all of physics. Before measurement, a quantum system exists in a superposition of all its possible states. The wave function describes these states and their probabilities. This is the quantum reality. After measurement, the system is in one definite state. The wave function has, in some sense, collapsed to a single outcome. This is the classical reality we observe. What happens in between? What is the mechanism of collapse? When exactly does the transition from quantum superposition to classical definiteness occur? And why does one specific outcome occur rather than another? These questions have been asked for a century, and no answer has won universal acceptance. The Copenhagen interpretation says, "Do not ask." The wave function is a calculational tool. Measurement is just measurement. There is no deeper question. The many worlds interpretation says, there is no collapse. All outcomes happen. The question is dissolved by multiplying the universe. Pilot wave theory says, there is no superposition. Particles always have definite positions. The wave guides them. The randomness is in our ignorance. Others say consciousness causes collapse, that it is the awareness of an observer, somehow, that causes the wave function to settle on a specific outcome. This is deeply controversial, and most physicists reject it, but it has never been definitively ruled out. And some say, the question itself may be wrong. Maybe the concepts of wave function and collapse and measurement are approximations, useful tools, but not fundamental descriptions of a deeper reality we have not yet found the language to describe. The measurement problem is a window into the most fundamental question in physics. What is real? Not what we can calculate, not what we can predict, but what actually exists, independent of observation, independent of measurement, independent of us. A century of quantum mechanics has not answered this, and the question remains as open, as urgent, and as strange as it was when Einstein and Bohr argued about it in the 1920s. Quantum mechanics changed the course of human civilization. This is worth saying clearly because quantum physics can feel abstract, like something happening in a laboratory, remote from daily life. But quantum mechanics is not remote from daily life. It is the foundation of modern life. The transistor, the semiconductor device that makes possible every electronic computer, every smartphone, every digital system, was invented by physicists who understood quantum mechanics. Without quantum mechanics, there are no transistors. Without transistors, there are no computers. The laser, which is used in medical procedures, in communications, in manufacturing, in scientific research, in the barcode readers at every checkout counter, operates on quantum mechanical principles. The stimulated emission of radiation, from which the acronym laser is derived, is a quantum process. Without quantum mechanics, there are no lasers. MRI machines in hospitals use a quantum effect called nuclear magnetic resonance to image the inside of the human body without radiation. Without quantum mechanics, there is no MRI. Atomic clocks, which underpin GPS navigation and are the most accurate timekeepers ever made, depend on the precise quantum transitions of atoms. Without quantum mechanics, there is no GPS. Solar cells convert sunlight into electricity through the photoelectric effect, the same quantum phenomenon that Einstein explained in 1905 and that won him the Nobel Prize. Without quantum mechanics, there is no solar energy. Every technology that distinguishes the 21st century from the 19th century rests on quantum mechanics. The quantum world is not abstract. It is the invisible architecture of the world we live in. Quantum mechanics asks us to change what we mean by reality. This is perhaps the deepest consequence of all. For most of human history, the assumption has been that reality is objective, that objects exist independently of being observed, that a particle has a definite position whether or not anyone is looking, that the moon is there when no one is watching. Quantum mechanics challenges this assumption in a way that has never been fully resolved. Particles do not have definite positions before they are measured. The position only comes into existence or becomes definite through the act of measurement. The wave function, which describes the particle before measurement,
is not a description of ignorance about a pre-existing position. It is a complete description of a reality in which position is genuinely undefined. What does this mean for ordinary objects? For the moon? For the chair you're sitting on? Decoherence explains, in part, why macroscopic objects appear to have definite properties. The constant interaction between large objects and their environments causes quantum superpositions to decay so rapidly they are unobservable. The chair is effectively always measured, constantly, by every photon that bounces off it and every air molecule that touches it. But the question of whether this means the chair really has a definite position, or merely appears to, is a question that different interpretations of quantum mechanics answer differently. And this is not a question about chairs. It is a question about the nature of reality. Whether the universe has a definite state independent of observation,
whether there is a fact of the matter about the world that exists, whether or not any observer is present. Quantum mechanics does not give us a clear answer. It gives us a mathematical framework that predicts what we will observe with extraordinary accuracy, while leaving deeply open the question of what is there when we are not observing. Perhaps reality is relational, existing only in the interactions between things. Perhaps it is many, branching endlessly into parallel versions. Perhaps it is guided, determined at a deeper level by a physics we have not yet found. Perhaps the question itself is malformed, and reality is simply a word we use for the patterns in our observations. Quantum mechanics has made these questions concrete. It has turned philosophy of reality into physics of reality, and it has not yet provided the answer. Let your breathing slow now. Let the strangeness settle. You have been somewhere very unusual tonight. You have been in the world where particles are waves and waves are particles, where observation changes what is real, where particles tunnel through walls and exist in all their possible states at once, where two particles can be connected across any distance, where empty space fluctuates with energy, where the future is genuinely open, where birds navigate by quantum spin and plants harvest sunlight with quantum coherence. You have been in the quantum world, the world that underlies everything else, the world that all of ordinary experience is built upon, resting on foundations that do not behave like anything ordinary experience would lead you to expect. And yet, here you are, in a body built of quantum particles, lying in a room built of quantum fields, breathing air made of quantum atoms, thinking thoughts that are, at some level, patterns of quantum events in the neural matter of your brain. You are a quantum system, not in a mystical sense, in a physical one. The atoms in your body obey quantum mechanics. The electrons that carry signals between your neurons tunnel through quantum barriers. The proteins in your cells change shape through quantum processes. The chemistry of life is quantum chemistry. The strangeness is not out there in a laboratory. It is here, in you, in every breath and every heartbeat, and every moment of awareness. And that strangeness is not threatening. It is simply the depth of what things are, a depth that goes all the way down, a depth that still surprises the physicists who have spent their lives studying it. You are a collection of quantum fields, arranged by the laws of physics and the long process of evolution into a form that can ask questions about quantum fields. A form that can feel wonder at the quantum uncertainty at the heart of its own existence. A form that can lie in the dark and think about wave functions and superposition and entanglement, and find these thoughts not frightening, but beautiful. The universe is stranger than it needs to be. This is a thought that physicists sometimes have. The universe could have been simpler. The laws of physics could have been plainer. Quantum mechanics could have been unnecessary, could have been replaced by some clean, intuitive, classical description of particles moving through space with definite properties. But it isn't. The universe chose, if we can use that word, a stranger path. A path in which particles are probability clouds, in which observation shapes reality, in which entangled particles are connected across any distance, in which empty space fizzes with virtual particles.
It was forced on physics by reality. Atoms were once thought to be the smallest things in existence. The word atom comes from the Greek atomos, meaning indivisible. The ancient Greek philosophers Democritus and Leucippus proposed that matter was made of tiny, indivisible particles separated by empty space. This was a remarkable intuition, made without any experimental evidence, purely through philosophical reasoning about the nature of matter. For 2,000 years, atoms remained a philosophical concept. Then, in the 19th century, chemists began to find experimental evidence for them. The laws of chemical combination, the fact that elements combine in fixed ratios by mass, implied the existence of discrete units. John Dalton formalized the atomic theory in 1808, but the atoms of Dalton's chemistry were still featureless spheres, indivisible, structureless, the smallest things. Then came the electron. J.J. Thomson discovered it in 1897, a particle thousands of times lighter than the lightest atom, carrying negative electric charge present inside every atom. Atoms were not indivisible. They had internal structure. Then came the nucleus. Ernest Rutherford bombarded gold foil with alpha particles in 1909 and found, to his astonishment, that some bounced almost straight back. The atom was mostly empty space with a tiny, dense, positively charged nucleus at its center. Then the nucleus itself was found to have structure, protons and neutrons. And then the protons and neutrons themselves were found to be composed of quarks, held together by gluons carrying the strong nuclear force. The story of quantum physics is partly the story of going deeper and deeper into matter, finding structure at every level, each layer smaller and stranger than the one above it, and each layer obeying not classical mechanics, but quantum mechanics. We do not yet know if quarks are fundamental. We do not know if there is a level below them. The Standard Model treats quarks and leptons, the family of particles that includes electrons, as fundamental. But the Standard Model may itself be an approximation of a deeper theory. The universe may have levels below the ones we know. The descent into the small may continue. And if it does, quantum mechanics, or something deeper, will be there at every step. Quantum cryptography offers perfectly secure communication. The uncertainty principle has a remarkable practical consequence. If you try to measure a quantum state without knowing what it is, the measurement disturbs the state, and this disturbance can be detected. Quantum cryptography uses this fact to create communication channels that are theoretically unbreakable, not because the mathematics of the encryption is too complex to crack, as in classical cryptography, but because any attempt to intercept the communication necessarily disturbs the quantum states carrying the information, and this disturbance reveals the presence of the eavesdropper. The most developed form of quantum cryptography is quantum key distribution. Two parties, traditionally called Alice and Bob in physics thought experiments, wish to share a secret key that they can use to encrypt their messages. They exchange a series of single photons, each one in a quantum state that encodes a bit of the key. If an eavesdropper, Eve, intercepts the photons to measure them, she inevitably disturbs their quantum states. When Alice and Bob compare a sample of their measurements over a public channel, they can detect the disturbances caused by Eve and know that their channel has been compromised. If no eavesdropping is detected, they can be certain their shared key is secure. It is guaranteed by the laws of physics, not by the difficulty of a mathematical problem.
Quantum key distribution has been demonstrated over distances of hundreds of kilometers through fiber optic cables and over thousands of kilometers using satellites. China has built a quantum communications network spanning thousands of kilometers. The technology is no longer purely theoretical. In a world where classical encryption may eventually be broken by quantum computers, quantum cryptography offers an alternative rooted not in mathematics, but in the fundamental laws of nature. The strangeness of quantum mechanics is becoming a tool for privacy. The uncertainty principle is becoming a guarantee of secrecy.
The Planck scale is where quantum mechanics and gravity collide. There is a length so small that our current theories of physics break down completely. It is called the Planck length. It is approximately 1.6 times 10 to the power of negative 35 meters. To give some sense of scale, a proton is about 10 to the power of negative 15 meters. The Planck length is 20 orders of magnitude smaller than a proton. At this scale, the energy density required to probe such small distances would be so extreme that, according to general relativity, it would collapse into a black hole. Space-time itself, at the Planck scale, is thought to be not smooth and continuous, but somehow granular, foamy, subject to violent quantum fluctuations. The Planck scale is where quantum mechanics and general relativity must somehow be unified, where a theory of quantum gravity must operate, and no such theory, confirmed by experiment, currently exists. String theory proposes that the fundamental entities are not point particles, but tiny vibrating strings of energy, whose different vibrational modes correspond to different particles. The strings vibrate in 10 or 11 dimensions, most of which are compactified at the Planck scale. String theory naturally incorporates a graviton, the quantum carrier of gravity, and is mathematically consistent. But it makes predictions that are currently untestable with any foreseeable technology. Loop quantum gravity takes a different approach, quantizing space-time itself, proposing that space is made of discrete loops of quantum geometry, and that the smooth space-time of general relativity is an approximation that breaks down at the Planck scale. Both approaches are mathematically sophisticated and intellectually serious. Neither has been experimentally confirmed. The unification of quantum mechanics and gravity, the final piece of the theoretical puzzle, remains unachieved. We do not know what happens at the Planck scale. We do not know what space-time is made of at its finest grain. We do not know what black holes look like from the inside, where the singularity predicted by general relativity would be smoothed out by quantum effects we cannot yet calculate. The quantum world still has its deepest secrets intact. There are particles that are their own antiparticles. Every fundamental particle has a corresponding antiparticle with the same mass but opposite charge. The antiparticle of the electron is the positron with positive charge. The antiparticle of the proton is the antiproton with negative charge. When a particle meets its antiparticle, they annihilate each other, converting their mass entirely into energy in the form of photons. This is the most efficient energy conversion possible, far more efficient than nuclear fission or fusion. Matter and antimatter were produced in equal amounts in the Big Bang, and yet the universe is made almost entirely of matter. Antimatter is extraordinarily rare. This is one of the deepest unsolved problems in physics. If the Big Bang produced equal amounts of matter and antimatter, why is there any net matter at all? Why did the matter win? The answer almost certainly involves some subtle asymmetry in the laws of physics that treats matter and antimatter slightly differently. A phenomenon called charge parity violation has been observed in certain particle decays,
confirming that the laws of physics are not perfectly symmetric between matter and antimatter. But the measured asymmetry is not large enough to explain the overwhelming predominance of matter in the universe. Something is missing from our understanding. But alongside the ordinary particles with their antiparticle partners, there exist particles that are their own antiparticles. These are called Majorana fermions, after the Italian physicist Ettore Majorana, who predicted them in 1937. The photon is a Majorana particle. A photon is its own antiparticle. For matter particles like electrons, Majorana fermions have been hypothetical. But recent experiments in condensed matter physics have found excitations in materials that behave like Majorana fermions. And physicists are attempting to use them to build qubits that are inherently protected from decoherence, a potential breakthrough for quantum computing. Ettore Majorana himself disappeared in 1938 at the age of 31 on a boat trip between Palermo and Naples. His body was never found. His fate remains a mystery, but the particles that carry his name persist.
At the intersection of quantum mechanics and the deepest questions about the nature of matter. Quantum mechanics makes the night sky possible. This is worth ending on. Not with the strangeness and the puzzles, though they are real and deep and will not be resolved tonight, but with gratitude of a kind. The stars exist because of quantum mechanics. Without the quantum tunneling that allows protons to fuse in stellar cores, there would be no fusion. Without fusion, there would be no stellar energy. Without stellar energy, there would be no light from the sky. The chemistry that makes life possible exists because of quantum mechanics. The electron shells of atoms, the way atoms bond to each other, the specific shapes of molecules, all arise from quantum principles. Without quantum mechanics, there is no carbon, no water, no proteins, no DNA, no cells, no life. The fact that matter is stable, that atoms don't collapse, that the chair holds your weight, that the ground doesn't fall apart beneath you, is a consequence of quantum mechanics. The Pauli exclusion principle, the uncertainty principle, the wave nature of matter, these are what hold the physical world together. The atoms in your body were forged in stellar interiors over billions of years, scattered by supernova, gathered by gravity, shaped by chemistry, organized by evolution, and arranged by processes that required quantum mechanics at every step into the form that is you. You are a quantum outcome. Not random exactly, not determined exactly. Something in between. Something for which we do not have the right words yet. Something shaped by quantum probability, by the collapse of wave functions across billions of years of cosmic and biological history, into this specific arrangement in this specific moment, thinking these specific thoughts. The quantum world made you possible. And you, in your curiosity, your wonder, your reaching toward understanding, are reaching back toward the quantum world that made you. That is a kind of beautiful recursion that requires no interpretation, no philosophy, no framework to stand in. Just the simple, extraordinary fact of it. The zero-point energy means nothing is ever truly at rest. Even at absolute zero, the coldest temperature possible, the temperature at which all classical motion ceases, quantum systems cannot be at rest. The uncertainty principle forbids it. If a particle were truly at rest,
its momentum would be exactly zero. But then its momentum would be precisely known, which would require its position to be completely uncertain, spread across all of space. A particle perfectly at rest is not a particle that can be said to exist anywhere in particular. The resolution is zero-point energy. Even at absolute zero, particles vibrate. They jitter. They fluctuate. Not because they have thermal energy, but because quantum mechanics demands it. The lowest possible energy of a quantum system is not zero. It is some small but non-zero value. The zero-point energy, the irreducible quantum buzz that fills the universe at every temperature, even the coldest possible. Liquid helium demonstrates this beautifully. At very low temperatures, most substances freeze into solids. The atoms slow down and lock into a crystal lattice. But helium remains liquid all the way down to absolute zero at normal pressures. It never freezes, because its zero-point energy is large enough relative to the weak forces between helium atoms to prevent them from locking into a solid. The quantum jitter keeps helium liquid forever. Solid helium can be made, but only by applying extremely high pressure, physically forcing the atoms close enough together that the zero-point motion cannot push them apart. The pressure overcomes the quantum restlessness. Nothing is at rest. Everything vibrates with quantum necessity. The silence at the heart of matter is not a silence at all. It is a constant, irreducible quantum hum, inaudible, immeasurable from the outside, but as real as anything in physics. The quantum eraser experiment suggests that the future can affect the past. This is one of the most unsettling experiments in quantum mechanics, and it is real. It has been performed. The results are what quantum mechanics predicts. The quantum eraser is a variation of the double-slit experiment. In the standard double-slit experiment, adding a measurement to detect which slit the particle goes through destroys the interference pattern. The act of gaining information about the particle's path causes it to behave like a classical particle rather than a wave. In the quantum eraser, the experimenter takes the information gained from the which path measurement and erases it. They set up the apparatus so that the information about which slit the particle went through is collected, but then destroyed before anyone looks at it. When the which path information is erased, the interference pattern returns. But here is the extraordinary part. In some versions of the quantum eraser, the which path information is erased after the particle has already been detected at the screen. The particle has already landed. Its position has already been recorded, and then the which path information from an entangled partner particle is erased. And when the results are sorted, those particles whose which path information was erased show interference. Those whose which path information was preserved do not. The particle seems to have known when it hit the screen whether its which path information was going to be erased in the future. Physicists are careful not to say that the future is affecting the past in a way that violates causality. The interference pattern only becomes visible after you sort the results based on what happened to the partner particles. And this sorting requires classical information that cannot travel faster than light. You cannot use the quantum eraser to send a message backward in time. But the correlations are there. The patterns are there. The mathematics is clear. And
And what it means in terms of the nature of time and causality at the quantum level remains deeply contested. The quantum eraser whispers something about the relationship between past and future that we do not yet have the framework to fully hear. Quantum mechanics is not intuitive because human intuition evolved for a different world. We evolved on the scale of animals and trees and rocks and rivers. We evolved to track moving objects, to judge distances, to recognize faces, to anticipate the trajectories of thrown stones. The physics that matters for survival at our scale is classical physics. The quantum world is simply too small to matter for the things our ancestors needed to do. Our intuitions are calibrated for a world of middle-sized objects moving at speeds much less than light. In that world, objects have definite positions. They take one path at a time. Measuring them does not disturb them. They do not tunnel through barriers. They do not become entangled with distant partners. This is why quantum mechanics feels strange. Not because it is wrong, but because our brains were not built to feel comfortable with it. We are cognitive instruments designed for the classical world, trying to understand the quantum world. And the mismatch produces the discomfort of the genuinely strange. Niels Bohr is said to have remarked that anyone who is not shocked by quantum mechanics has not understood it. This is still true. The shock is appropriate. It means you have grasped something real about the gap between the world we evolved to inhabit and the world that actually exists at its deepest level. But the shock is also temporary in a sense. Physicists who work with quantum mechanics every day develop a kind of quantum intuition, not classical intuition applied to small things. A different kind of intuition, built from years of calculating quantum systems and seeing how they behave, that allows them to navigate the quantum world with a feeling of familiarity that does not require it to make classical sense. You can become comfortable with the quantum world without it becoming less strange. Comfort and strangeness can coexist. And perhaps that is a lesson that extends beyond physics. Perhaps the capacity to remain comfortable with deep strangeness, to sit with the genuinely unknown and find it not threatening but interesting, is one of the most valuable things that thinking about the quantum world can teach. Every measurement is an act of creation. This is one interpretation of what quantum mechanics is telling us, perhaps the most radical one. Before a measurement, the quantum system is in superposition. It does not have a definite value for the quantity being measured. The value does not exist. And then, through the act of measurement, a value comes into being, not revealed, created. If this interpretation is correct, then observation is not passive. It is active. It does not merely discover pre-existing facts about the world. It participates in creating them. The observer and the observed are not separate. They are entangled in a deep sense by the act of measurement.
Some physicists, particularly those inclined toward the relational interpretation of quantum mechanics developed by Carlo Rovelli, take this seriously. They propose that quantum states are not absolute properties of systems, but relational properties. A particle does not have a spin of up or down. It has a spin of up or down relative to a specific measurement and a specific measuring device. Reality is constituted by interactions. Facts come into existence through relations. This is a long way from the picture of reality we begin with.
The picture of a world full of objects with fixed properties, sitting there in space, waiting to be observed. Quantum mechanics suggests this picture is not just incomplete, but fundamentally misconceived. The world may not be a collection of things. It may be a web of interactions, a network of relations, a process rather than a state. And what we call observation may be simply the participation of one part of the process in another. These ideas are speculative. They are philosophy as much as physics, but they are grounded in the actual mathematics of quantum mechanics, in the actual experimental results of a century of testing the quantum world. And they invite a different relationship with the act of noticing. Every moment of awareness, every perception, every thought may be, in some small quantum sense, an act of participation in the ongoing creation of the world. The quantum world is not finished surprising us. Every decade brings discoveries that no one predicted. Quantum computing, quantum biology, topological quantum states that encode information in the global properties of a system rather than in individual particles, making them robust against decoherence in ways that conventional qubits are not. New tests of quantum non-locality that push the boundaries of what we can demonstrate about entanglement. The Large Hadron Collider at CERN, the most powerful particle accelerator ever built, explores the quantum field theory of the Standard Model at energy scales never before probed. The Higgs boson, the quantum of the Higgs field whose interaction with particles gives them mass, was discovered there in 2012. Other discoveries may follow, discoveries that point beyond the Standard Model to a deeper quantum framework. Gravitational wave observatories detect the ripples in space-time predicted by general relativity, opening a new window on the universe. And theorists are already thinking about how to merge this new observational window with quantum mechanics, about what gravitational waves might reveal about the quantum nature of spacetime. Tabletop experiments are testing quantum mechanics at scales and in regimes that were inaccessible a decade ago. Quantum superposition has been demonstrated in objects large enough to see with the naked eye, pushing the boundary of where quantum mechanics gives way to classical behavior. The frontier of quantum physics is not closed. It is wide open. The century-old theory still has new territories to explore, new questions to confront, new experiments to perform. And in laboratories around the world tonight, as you rest, as you drift, physicists are doing those experiments. Graduate students are aligning optical equipment in the dark. Theorists are writing equations on whiteboards. Cryogenic systems are cooling quantum devices to temperatures colder than deep space. The conversation between human curiosity and quantum reality is continuing. The strangeness is not finished. The discoveries are not done. And somewhere in that ongoing conversation, in the equations not yet written and the experiments not yet designed, is the next layer of the quantum world, waiting to be found. Entangled particles and the mystery of non-locality continues to challenge us. When physicists say that entanglement is non-local, they mean something very specific and very strange. They mean that the correlations between measurements on entangled particles cannot be explained by any theory in which the particles carry predetermined answers with them from the moment of their creation. This was the content of Bell's theorem, and it has been tested in experiments of increasing sophistication since the 1970s. The most rigorous tests, called loophole-free Bell tests, were first performed in 2015. They closed every experimental loophole that had allowed skeptics to question previous results. And they confirmed, definitively, that the universe is non-local.
The particles do not carry hidden information. The correlations arise not from pre-existing properties of the particles, but from the quantum connection between them, a connection that persists across any distance, that operates instantaneously, that cannot be shielded or blocked or attenuated by any material. This non-locality is not a defect of quantum mechanics. It is not a gap in our understanding. It is a feature, a real, confirmed, experimentally verified feature of the universe at the quantum level. And it has implications that physicists are still working through. It suggests that the universe, at its deepest level, is not locally real in the way classical physics assumed. The information about an entangled system is not stored locally in one particle or the other. It is stored in the quantum state of the combined system, non-locally, in a way that cannot be decomposed into independent properties of the individual parts. In 2022, the Nobel Prize in Physics was awarded to 3 physicists who pioneered the experimental study of entanglement and the testing of Bell inequalities. Alain Aspect, John Clauser, and Anton Zeilinger. The Nobel Committee's citation noted that their work had established the violation of Bell inequalities and the genuine existence of quantum entanglement. Non-locality is now Nobel Prize Physics. It is not fringe. It is not speculation. It is confirmed reality. The universe is non-local at its quantum foundation. The relationship between quantum mechanics and consciousness remains one of the deepest open questions. Most physicists are skeptical of claims that consciousness plays a fundamental role in quantum mechanics. The measurement problem, the question of what causes the wave function to collapse, does not necessarily require a conscious observer. Any physical interaction that creates a record of a quantum event, any irreversible change in any physical system may suffice. And yet, the question persists. It persists because quantum mechanics places the act of measurement at the center of the theory, and because the theory does not itself define what a measurement is. This gap has been filled by some thinkers with consciousness, with the idea that it is awareness specifically that causes quantum states to collapse. John von Neumann, one of the architects of the mathematical formalism of quantum mechanics, developed a chain of reasoning about measurement that some have interpreted as implying that the chain of quantum interactions involved in a measurement process does not terminate until it reaches a conscious observer. Wigner's Friend, a thought experiment proposed by the physicist Eugene Wigner, explores the paradoxes that arise if 2 conscious observers have different wave function descriptions of the same quantum event. Penrose and Hameroff have proposed a specific mechanism by which quantum processes in microtubules inside neurons might give rise to consciousness in a way that is fundamentally quantum, not classical. Their theory, called orchestrated objective reduction, is controversial and has attracted both serious interest and serious criticism. These ideas remain highly speculative. The mainstream view in physics is that consciousness is not fundamental to quantum mechanics, that decoherence and the practical indistinguishability of quantum from classical behavior in macroscopic systems is sufficient to explain what we observe without invoking consciousness. But the mainstream view has not fully solved the measurement problem, and until it does, the question of consciousness and quantum mechanics will remain open. Not as mysticism, not as wishful thinking, but as a genuine scientific and philosophical puzzle
at the intersection of the two deepest mysteries we face: the nature of the physical world and the nature of mind. You are a quantum observer. Not in the sense of the Copenhagen interpretation, not in the sense that your consciousness collapses wave functions, though perhaps in that sense too, if the relevant interpretations are correct. But in a simpler and more concrete sense, you observe. You take in information about the world, and every act of taking in information, every photon that enters your eye, every air pressure wave that moves the fluid in your inner ear, every chemical molecule that binds to a receptor in your nose or tongue is a quantum event. The transduction of sensory information into neural signals is chemical and electrical, and chemistry and electricity are quantum mechanical at their foundation. Your brain processes the information from these quantum events. It builds a model of the world.
It represents a reality that is, in the terms of physics, a classical approximation to the underlying quantum reality. The world you see and hear and smell and touch is not the quantum world directly. It is the classical picture that your senses construct from quantum signals, smoothed and averaged and decoherence processed into something your classical scale brain can work with. You live at the boundary between the quantum and the classical. Below you, quantum. Above you, classical. And you sit at the transition. A biological machine exquisitely calibrated to extract the relevant features of the quantum world and present them as a navigable classical reality. This is not a limitation. It is an extraordinary achievement of 4 billion years of evolution. The ability to extract the relevant signal from the quantum noise, to build a reliable, consistent, useful model of the world from the uncertain, superposed, entangled events at its base. You are an interpreter of the quantum world, and what you interpret it as, what you experience it as, is this room, this moment, this breath, this rest. Quantum mechanics will not be the last word. No scientific theory has ever been the last word. Newton's mechanics was the final theory of motion, until it wasn't. Classical electromagnetism was the complete theory of light and electricity, until quantum mechanics showed it was an approximation. General relativity is our best theory of gravity, and it is extraordinarily accurate. But we know it cannot be complete because it breaks down its singularities and cannot be reconciled with quantum mechanics. Quantum mechanics itself, the most successful theory in physics, is almost certainly not complete. Not because it is wrong about the things it predicts. Its predictions are right, but because it cannot be the whole story. It does not include gravity. It does not explain why there is more matter than antimatter in the universe. It does not tell us what dark matter is. It does not explain the specific values of its own constants, the charge of the electron, the mass of the quarks, the strength of the fundamental forces. A deeper theory exists. Not a theory that will prove quantum mechanics wrong, but a theory that will explain why quantum mechanics has the form it does, that will derive its strange rules from something more fundamental, that will unify it with gravity and explain the features that quantum mechanics takes as given. We do not know what this theory is. We do not know when it will be found. We do not know what it will look like, whether it will be recognizable as an extension of what we have, or something as conceptually radical as quantum mechanics itself was relative to classical physics. But it is there, somewhere in the logical structure of the universe, deeper than what we have found, There is a framework that contains quantum mechanics as a special case and reaches beyond it into territory we have not yet mapped. And the physicists who find it, if they have not already been born, are being born now, or will be born, into a world shaped by quantum mechanics, educated in quantum mechanics, standing on quantum mechanics as a foundation, ready to see past it to whatever is next. The story of quantum mechanics is one of the great intellectual adventures in human history, and it is not finished. The next chapter is being written now, in laboratories and in notebooks, and in the quiet, focused thinking of people who find the quantum world not frightening, but irresistible. As you drift toward sleep now, carry this thought gently with you. The universe, at its deepest level, is not made of solid things. It is not made of matter in the intuitive sense. It is made of quantum fields, shimmering with uncertainty, structured by probability, connected by entanglement, in ways that span any distance. And from this shimmering, uncertain, entangled foundation, everything solid and familiar and reliable has emerged. The chair beneath you, the ceiling above you, the air in your lungs, the signals moving through your nerves right now, carrying the sensation of rest, of warmth, of heaviness in the limbs. All of it is quantum mechanics expressing itself at the scale of your life. The quantum world is not something separate from you. It is not something distant or abstract. It is the texture of everything. It is what the world is made of, all the way down. And what you are made of, all the way down, is the same thing. You are not separate from the strangeness. You are an expression of it, a particularly complex, particularly self-aware expression of quantum fields that have organized themselves over billions of years into a form that can wonder about their own nature. That is extraordinary. That is the kind of thing that deserves a moment of quiet appreciation before sleep. The sheer remarkable strangeness of being a quantum system contemplating quantum mechanics. The part of the mystery, studying the mystery, feeling something that might be called awe at the mystery, from inside it. Rest now. The quantum world will keep its business through the night, without requiring your attention. And in the morning, it will still be there, still uncertain, still entangled, still tunneling and fluctuating and shimmering with the irreducible quantum nature of everything. Still extraordinary, still here. Schrödinger's equation describes how quantum states evolve through time. It is, in some ways, one of the most beautiful equations in physics. Erwin Schrödinger wrote it down in 1926 after a weekend of intense mathematical work, and it became the central equation of quantum mechanics. The Schrödinger equation describes how the wave function of a quantum system changes over time. Given the wave function at one moment, the equation tells you exactly what it will be at any later moment. This evolution is perfectly deterministic. The wave function evolves smoothly, continuously, and predictably. The randomness in quantum mechanics does not come from the Schrödinger equation. It comes from measurement. When a measurement is made, the smooth, deterministic evolution of the wave function apparently ends, and a single, random outcome is selected with probabilities determined by the wave function. This is the collapse.
and the Schrödinger equation has nothing to say about it. This gap between the deterministic evolution and the random collapse is at the heart of the measurement problem. Two different rules seem to apply to quantum systems. One rule when they are evolving freely, another rule when they are measured. And the theory does not explain when the transition between rules occurs, or why it occurs, or what mechanism causes it. The Schrödinger equation is continuous and deterministic and beautiful, and it does not tell the whole story. Some interpretations, like many worlds, say the Schrödinger equation is the whole story, that there is no collapse, that the apparent randomness of measurement is an artifact of the perspective of a particular observer in one particular branch of the branching universe. Others say the Schrödinger equation must be modified, that there is a deeper equation that reduces to Schrödinger's in most circumstances, but produces collapse in others. And others say the Schrödinger equation describes quantum states relative to a particular observer, and the apparent contradiction between its deterministic evolution and the random collapse dissolves when we understand that different observers have different descriptions. The equation is clear. What it means remains in question. Virtual particles borrow energy from the vacuum and pay it back immediately. In quantum field theory, the uncertainty principle applies not just to position and momentum, but to energy and time. The more precisely the energy of a system is known, the less precisely the time of that energy state can be defined, and vice versa. This has a remarkable consequence. For very short periods of time, energy can appear to fluctuate beyond what classical physics would allow. Virtual particles can pop into existence, borrowing energy from the quantum vacuum, and then annihilate again, returning the energy before the uncertainty principle debt comes due. These virtual particles are not directly observable. By definition, they exist and disappear within the time allowed by the uncertainty principle before any measurement could detect them. But they have real, measurable effects on other particles that interact with them. The Casimir effect, the attraction between closely spaced metal plates in vacuum, is caused by the suppression of virtual particle fluctuations between the plates. The Lamb shift, a tiny displacement in the energy levels of the hydrogen atom that puzzled physicists in the 1940s and was crucial in the development of quantum electrodynamics, is caused by the interaction of the electron with virtual photons. The magnetic moment of the electron, measured and calculated to 11 decimal places, differs from the simple quantum mechanical prediction because of the electron's interaction with a cloud of virtual photons and virtual electron-positron pairs that perpetually surround it.
Virtual particles are real in their effects, even if they are never directly observed. The quantum vacuum is not empty. It seethes with activity that never quite surfaces into observation, but never quite disappears either. The boundary between something and nothing in the quantum world is not sharp. It is blurred. The vacuum is not nothing. Nothing is nothing at the quantum level. Something is always happening. Quantum mechanics has been tested more rigorously than any other theory in history. This deserves to be said clearly, because the strangeness of quantum mechanics can make it seem like speculation, like philosophy dressed up in mathematics, like something that physicists believe for aesthetic or cultural reasons, rather than because it has been proven. Quantum mechanics has been tested relentlessly for a century, in experiments of every kind, in every domain of physics, at every scale, from subatomic particles to atoms to molecules to condensed matter systems.
Not a single experiment has produced a result that contradicts quantum mechanics. The precision of some of these tests is breathtaking. The magnetic moment of the electron, a quantity that quantum electrodynamics predicts through calculations involving virtual particles and quantum field fluctuations, has been measured and calculated to agree to better than 1 part in a trillion. To get an idea of the precision, this is equivalent to measuring the distance from New York to Los Angeles and getting the right answer to within a fraction of a millimeter. The double-slit experiment has been performed with electrons, neutrons, protons, atoms, molecules, and increasingly large objects. Interference patterns emerge every time. The wave nature of matter has been confirmed at every scale we can access. Bell inequalities have been tested with photons, electrons, atoms, and systems of many particles. They are violated in every case, confirming quantum non-locality. Quantum tunneling predictions match experimental measurements of radioactive decay rates, tunneling microscopy currents, and chemical reaction rates to high precision. Quantum mechanics is not believed on faith. It is not believed because it is elegant, though it is. It is believed because it has been tested and tested and tested again, and it has never been wrong. The strangeness is not a reason to doubt it. The strangeness is what nature actually is. The night settles around you now. Your breathing has found its own slow rhythm. Your thoughts are moving more gently, more loosely, the way thoughts move when the mind is giving up its grip on the day. You have been somewhere extraordinary tonight. You have been in the quantum world, and the quantum world has been in you, as it always is, as it always has been, as it will be long after this particular arrangement of quantum fields has dispersed and become part of other arrangements. The electron in its probability cloud, the photon choosing its path only when observed, the entangled particles, separated by any distance, still reflecting each other in measurements we cannot explain without accepting that the universe is genuinely, irreducibly strange. These are not stories about a world separate from yours. They are stories about the world you are living in right now. The world your body is built from. The world that your senses are translating, moment by moment, into the experience of lying here, of breathing, of resting, of drifting. The quantum world does not stop at the boundaries of laboratories. It does not suspend itself while you sleep. It continues beneath everything, at the level of everything, as the invisible and extraordinary foundation of all that is. And you are part of it, not passively, actively, as a quantum system that observes, that interacts, that makes measurements simply by being alive and responsive to the world. Every photon your eye absorbs, every molecule your breath exchanges with the air, every electrical signal that moves through your neural tissue. Quantum events, all of them. You are participating in the quantum world even now, even in sleep, even in the quietest and most private moment of rest. And that participation, that being part of the quantum fabric of the universe, does not require you to understand it. It does not require you to hold on to any of what you heard tonight. The quantum world carries you whether or not you know its name. Sleep. Let the quantum world do its work. It knows what it is doing. It has been doing it for 13.8 billion years. It is very good at it. Good night.